Ethereum. For the last decade or two, or for the decade or two before Bitcoin, people were trying to build different digital money systems, and many succeeded, but there was one central flaw, in that resulted from something called the double spending problem. So essentially, there was no way to ensure that people didn't double spend their digital tokens. Um, Louder? Sorry. There's no way to ensure that people didn't double spend their digital tokens without having a centralized database to make sure that wasn't done. So in November 2008, a person or a group named Satoshi Nakamoto wrote a white paper called Bitcoin, which basically solved the double spend problem. So in a decentralized way, the algorithm presented enabled digital money to be created. January 3rd, 2009, it was released. So Bitcoin built on some technologies and implemented essentially the first use case of those technologies, which is transmission and storage of value, or a money system. An inventor named Vitalik Buterin was working on the Bitcoin project, working on many other projects, Bitcoin 2.0 projects, to try to bring more functionality to that sort of system beyond just money. So he worked on many different projects in the space and realized that a lot of smart people weren't making much progress. And so he took a step back and wrote a white paper called basically Ethereum. And a bunch of people gathered around that white paper and essentially formed the Ethereum project. So in late January 2014, we all met, formed the project, and it was announced. Vitalik did a presentation. So about 6-7 months ago, July 30th, 2015, this group actually released the first version of Ethereum. It is a fully fledged operating version of Ethereum, and people are building on it now. The interesting thing about it was that it embodies a principle of decentralized organization, essentially in opposition to top-down command and control. And the way it came to life was basically in the same way. It's self-organized. So the Ethereum Foundation put out the code, people downloaded it. In order to fund the project, we conducted a sale. We sold the token Ether for Bitcoin, and all of the receipts, 9,000 different receipts, were actually stored in a decentralized way on the Bitcoin blockchain. So in order to construct the Genesis block, the beginning of the Ethereum project, the Ethereum developers created a mechanism whereby everybody who wanted to could download the Ethereum client, build the Genesis block themselves, and then start these things running, and they would reach out into cyberspace and connect with one another, and essentially it formed itself. 6 months later, success. There are thousands of developers around the world. People are being asked to speak at conferences like Lyft, and the token itself is actually doing quite well. It has become basically number 2 behind Bitcoin in terms of total transactions and the size of the monetary base. So Ethereum has essentially built the world's first world computer. Its capabilities arise from the same 5 components that enable Bitcoin. These things are a blockchain database, so that's essentially a database of blocks of transactions that lead all the way back to the start of time, basically 6 months ago. And this database is a shared resource. It's a next generation kind of database. It presents, or it contains transactions that are time-stamped, contains transactions or data and programs that are shared, and it's a non-repudiable and transparent database. The second element is the cryptographic token. These are based on public key cryptography, so essentially private keys and public keys. They're very similar between Bitcoin and Ether or Ethereum. Both systems have a peer-to-peer network architecture. So this turns the paradigm of client-server computing to one in which every node on the network is both a client and a server. So it decentralizes processing and makes it so that there isn't a single point of vulnerability or control. Both systems have a consensus formation algorithm, so that essentially involves processors around the world processing transactions and all agreeing on exactly what happened and when. In Bitcoin, it's what happened and when with respect to transmission and storage of value. In Ethereum, it's what happened and when with respect to the execution of shared programs, and can also do what Bitcoin does, transmission of storage and value. The essential differentiating element between Bitcoin and Ethereum is what you can do on it. And that's enabled by the virtual machine and the programming language. In Bitcoin, there's a very simple virtual machine at each node and a very simple programming language. You can only write a very limited class of programs. On Ethereum, there is a general purpose computer or virtual machine at each node and a very rich programming language. So you can write whatever you can dream up, essentially. It is possible to build decentralized applications on top of and outside of the Bitcoin protocol. Essentially, when you do that, you're sharing the data, but there is no real way to share the program, so you can't really know that a specific program or process is operating to affect that data. Those things would have to be on a centralized server somewhere. So Ethereum's core value with respect to Bitcoin is that, unlike Bitcoin that requires specialist programmers to stack up cryptographic primitives outside of the protocol to try to keep things secure, if they're trying to do something semi-sophisticated, for Ethereum, average programmers can build sophisticated, decentralized applications taking advantage of the full security of the protocol. So to a software developer, an average software developer, the dev process looks very similar to building a web application or a mobile app. So these 5 components together are a global computational resource because these networks are, by definition, globally accessible. The upgraded components enable Ethereum to enable configurably transparent, non-repudiable, and uncensorable, trust-minimized, pseudonymous usage of shared programs on this shared infrastructure. So to this decentralized computational substrate, if you add decentralized storage in the form of things like IPFS, the interplanetary file system, and different kinds of bandwidth, whether it's centralized bandwidth or decentralized mesh bandwidth, you get the world computer, or what we like to call the Ethereum world computer, which is transparent, deeply secure, it's uncensorable, it's unstoppable, it's non-repudiable, and elements on it are natively interoperable. So programs can access data from other programs very, very easily, provided they have permission, of course. So the Ethereum world computer represents a strong cryptographic foundation for building systems, building world systems. Essentially, these systems are based on the principle that code is law, rather than having to rely on legal, business, jurisprudence, and other types of systems that essentially operate in a top-down command and control type of context. Those sorts of systems lead to siloing of information and over-concentration of power. So the essence of Bitcoin, or the essence of blockchain, Bitcoin and Ethereum, is that different actors with different concerns can interoperate with one another in business processes embodied in smart contracts on that blockchain in a way that they can fully trust. This is revolutionary. Because everybody maintains their own local copy of the database and the programs, there is no opportunity for one person, a rogue system administrator, a CFO, to get in there and manipulate the numbers from 6 months ago. So challenges and roadmap for Ethereum, adoption. We've thought about many different aspects of it, but it seems to be happening. There's a lot of press. There are thousands of developers around the world that are building software for Ethereum and releasing software for Ethereum. These are small independent projects. These are big corporations, and it's happening. There are also hundreds of companies that are talking to organizations like ours to help them understand their blockchain strategy and build software for them. So scalability is the major challenge for blockchains. At Ethereum, there is a scalability solution that's been worked on for over a year. It involves proof of stake, moving from the consensus formation algorithm called proof of work to one called proof of stake, and it involves sharding of the address base. So without getting too technical, these things, there are proof of concepts that have been written to get this done. So what is Consensus? Consensus is a company I started about 16 months ago. There are currently 70 people working there on 4 continents. We build decentralized applications. We maintain a bunch of core infrastructure, so that's the Ethereum client and developer tools. And we have a professional services arm called Consensus Enterprise that does consulting work. What is a decentralized application? It's essentially a set of smart contracts on a blockchain and user interfaces for accessing those things. And the way that the user interface interacts or enables the user to interact with those things is by presenting the user with text fields, numbers, etc., choices, a go button or an execute button, and then that user interface packages up a transaction, asks the user to sign it, and it gets injected into the blockchain network. And it finds the contract or the smart contract that it's supposed to execute, and execution happens. So at Consensus, we're building a bunch of decentralized applications. We think of a bunch of these things as core components. They are wallet identity, reputation systems, registry systems, token issuance and management systems, decentralized exchange, a glue system for linking different blockchains together. We built a decentralized application store. We built an Ether browser, which enables you to access dApps from within a regular browser. Essentially, we think of these things as a economic, social, and political operating system, components that can be used by other applications or platforms of software as the core building blocks. So on top of this core, we built a triple entry general ledger system. We built a smart document formation and management system. We're building a decentralized Reddit or a threaded discussion system. We built Boardroom, which is a governance tool, and Wayfund, which is a crowdfunding platform. Handful of other things are being built. We're also building open industry platforms. So these things, essentially, we define some roles, and then we invite lots of people and businesses to fill those roles and interoperate on the system. And identity systems and reputation systems make all of that feasible. Some of these that we built are a prediction markets platform, an event and community management platform, a loan platform. We built Ujo Music, which enables artists to register content, attach usage policies to that content, and then consumers or other artists can pay for those licenses, and payment is achieved in real time. We're about to have our first provably fair decentralized hand of Ether poker. Two platforms, which I'll talk about more in a minute, are called resource generation platforms. One's an open energy markets platform, one's a community-supported agriculture platform. So some implications for all of this. Future of business process architectures. To us, the world looks like companies with private blockchains on which they put their business processes. A company would then define use cases and partners in other companies and create a partner blockchain or a consortium blockchain, and then some of their use cases or business processes would be appropriate for the public Ethereum network. Future of identity. Identity is really messed up. Many people don't have it. Many people spoof it. Essentially, we are building something called Uport, which will enable self-sovereign identity. It'll enable you to control your own personal data. You can release it in any sort of situation that you want to release it. It'll be configurably private. Uport also allows you to hold tokens of value. So it's basically an endpoint for a lot of different things that you'll be able to do on this new decentralized web that we're creating. Next generation financial industry infrastructure. We built a smart document formation management system. We build smart contracts that embody business processes that can be represented as essentially state transition graphs where the different counterparties sign off on different state transitions to model the flow of a business process. And we've built Balance, which is a triple entry accounting or general ledger system. So this will enable a financial industry infrastructure which can have real-time comprehensive auditing, real-time risk metrics, sensitivity analyses. We will enable the tracking of provenance of different elements in this system, so commodities, pharma, food, etc. We're building dashboards that will enable regulators, that will enable companies to track all of their activities on the blockchain, and also regulators to have a view of that. And regulators will be able to slice up the different views and have a real-time sense of the flows in a regional, sector, or global economy. Implications for secure IT infrastructures. Current infrastructures essentially have valuable components in the center protected by firewalls. This is a bad architecture, and it is regularly penetrated. Thefts are common. Destruction is common. This sort of infrastructure puts business processes on a blockchain. Access is in the identity portal, and every single transaction in that sort of infrastructure is a cryptographically secure transaction in which the user is authenticated and the user is authorized granularly for each business process. Future of moneyless commerce. If you tokenize assets and resources, you enable barter systems that are lightweight. You don't need to carry around the things that you're trading. And if you have ubiquitous exchange rates, everybody can pay with the tokens that they want to pay with, and everybody can receive the tokens that they want to receive. I can have 100 tokens that I prioritize to pay with. You can have 200 tokens that you would accept, and our agents figure out exactly how to do that transaction. You may need a third party in there sometimes to do an exchange in an intermediary token. So resource generation platforms and moneyless commerce. We built an open energy markets platform. We built a community-supported agriculture platform. Both of those have generators. Photovoltaic arrays are the generators in the decentralized energy platform, and farms are the generators in the agriculture platform. The resources are tokenized kilowatt hours and tokenized apples or potatoes. And essentially, those systems can be used in a spot market where people buy the tokens and trade them for kilowatt hours or other products, or futures and options can be issued so that consumers can provision for their resources over a certain period of time. So these platforms, these blockchains will constitute a mesh of what we believe will be smaller interacting business concerns, and we look forward to a day in which Mary can send some kilowatt hours across or send some electrons across the street to Bob, get paid for it in Apple tokens, and that's it. Thank you.
Thank you, Joseph, for this very educative presentation. So what we'll be doing, I didn't mention it, is we will just have a few questions, just to go maybe deeper in some of the topics that you wanted. So you have a link that you can find on the Twitter, and you can ask the question, and we'll receive it and choose the question by themselves. So one first thing that I found very interesting when we met with you almost 1 year ago now, and what the Ethereum community has been trying to build is, from the public standpoint, it's very technical. It's like almost a gibberish or like crypto something. Yes. But what you are trying to do is to bring it not to the technical people, but to open and more traditional industries. So can you just talk about a little bit more about how can your work be used by anyone in the room in a very simple way?
It's a complicated question. We are building different applications that are consumer focused. So poker, prediction markets. We're building a special kind of prediction markets that focuses on the entertainment industry. We think that will be an interesting access point. Crowdfunding platforms, lending platforms. There will be lots of ways for individuals to get involved. We're also, our anticipation is that adoption won't be really fast, but we are seeing a lot of businesses interested in understanding blockchain, figuring out how to make certain processes more efficient, or even set up new business models. So I think there will be a lot of that activity over the next few years.
And so my last question, my last question about the business model is how does Consensus is working from a business standpoint? Because the model you are trying to apply is quite interesting, no?
We think it's interesting, yes. So Consensus is a group of developers and other personnel. Everybody, we're still working through the details of this process, but essentially everybody owns a piece of Consensus, and there are many quasi-independent projects that are actually quite interdependent, because everybody needs the identity project, everybody needs the reputation project, and each one of these projects is potentially capable of spinning themselves out into an independent company. The core people of each project own direct equity in their own project, and everybody owns equity in the hub, which also owns a lot of equity in all those projects. So everybody owns a piece of everything that they're working with. It fosters communication, collaboration. It gives entrepreneurs diversification of their portfolio, and we think it will keep us together for a long time.
Cool. Yeah. Thanks so much again for coming and bringing us all these kind of interesting topics. Thanks.
There was a project called Namecoin, which was trying to make a blockchain-based domain name system. In 2013, there were projects called Colored Coins, which were trying to digitize arbitrary digital assets or arbitrary assets and put them on the blockchain. There were protocols called Mastercoin that were trying to integrate all sorts of fairly complex features. So there was a consensus that you can do lots of different really cool things with Bitcoin, or with other blockchains. Asset issuance, crowdfunding, title registration, lots and lots of stuff. Problem is, most blockchain protocols were designed like this. Pocket calculator, single purpose device, works reasonably well for all you care about is adding and multiplying numbers, but it does nothing else. And sure, someone with an advanced computer science degree with a good calculator can kind of hack it to play a video game inside of it, but do you really want to do that? So, after this, in 2013, there were people who were making protocols that looked like this. So Swiss Army knife. Basically, you come up with a list of 10 or 20 features he wants to have, make a little tiny thing for each one of them, stick them together into a knife, and there you go, that's your product. Or in this case, that's your blockchain. So back at the end of 2013, there were lots of projects that looked like this. They just said, okay, we want blockchains to be usable for asset issuance, crowdfunding, bets, prediction markets, identity registration, title registration. Pick a list of 20 different things, have a list of 20 different transaction types, and have a little piece of the protocol that supports each one. So this is all well and good. Problem is, what if you come up with your list of 20 applications, publish a protocol, then the next day some guy says, oh look, I discovered a 21st blockchain application. How am I going to fit it in? And in 2013, this is exactly what started to happen. So this is the Ethereum way. So why do we love smartphones so much? Basically because a smartphone is nice and generic. You buy it once, and download immediately comes with 50 or 100 applications. If someone comes up with a new application, they write the code, they upload it to the Google App Play Store, and if you want it to be accessible in China, you can upload it to the Huawei store as well. And then if anyone wants to use your application, they don't need to buy a new phone, they don't need to buy a new hardware dongle, they just download the app and they can start immediately running it. Very simple. And the cost of actually developing an application, all you have to do is write code. You don't have to make your own hardware, you don't have to have your own manufacturing, you don't have to have your own distribution. Just write a piece of code, upload it, and let people download it, and you're done. So this is the kind of abstraction and simplicity that I wanted to bring to the blockchain world with Ethereum. So Ethereum is a blockchain. I'm sure if people here are familiar with blocks, I'm sure people here are familiar with transactions. And these are all well and good, but Bitcoin has them too. Namecoin has them too, Litecoin has them too, Dogecoin has them. I'm not sure if Paycoin has blocks though. I don't know, Paycoin might even run on a server, I haven't even checked. Proof of server, the best kind of POS. But we have a few tiny additions. So the main thing that makes Ethereum tick is this built-in programming language. So basic concept is, if you have some new kind of application, then what you would do is you would write the rules of your application in a piece of code. Take this piece of code, you would call this a contract, upload it to the blockchain, and now you have a special type of account. And this type of account sits on the blockchain, and anyone can send a transaction to this account in order to interact with this account. So two types of account. One type of account is a user account, controlled by people like you. And the other type of account is a contract, which is controlled by a piece of code. If you send 1 unit of Ether to an account that is controlled by code, then no person controls it anymore. The only thing that can actually move that Ether is the execution of that contract's code itself. So it basically is an automaton sitting on the blockchain that's executing exactly as the code on the blockchain says it's going to execute. So this is all well and good. Let's try an example. So the hello world of Ethereum is sort of basic, a minimal sort of DNS system. So the idea here is you want to store a mapping of basically domains. So you have something like I don't know, Vitalik.eth, George.eth, Ethereum.eth, ask me about my cool Ethereum hacking services.eth. So you have a bunch of domains that people might want to register, and for each one you want to store the IP address that it points to, and you want to store who owns that domain at that particular time. So we have two functions. One of them is for registering a domain, and the logic is pretty obvious. If the domain has not yet been registered, then you set the owner to yourself. And another function that says set the IP address. If you own a domain, then you can set the IP address. And this is like basically the minimal thing that's like all you need in order to have like a maximally simple domain name system. Now, as I understand, Nick Johnson is going to be presenting about a kind of much more complete and better one at some point over the next 3 days, but this is sort of the kernel. This is what you start with. So you have this piece of code. Then what you would do is you would compile it. You would get some bytecode, then include the code in a transaction, push the transaction up onto the blockchain. Now what you have created is a contract. And a contract has an address. It has some 20-byte string that represents sort of the location of the contract. It will look like 0x357c, whatever. If you want to register a domain, what you would do is you would send a transaction, and you would specify this transaction is going to be talking to this contract. Now, What can the transaction do? Well, it can try to register, or it can try to set the IP address. So let's say you want to register a domain. What you would do is, in the transaction, you would encode some information that says, I want to call the register function, and I want to call the register function with like some particular piece of data, like, I don't know, george.eth or whatever. Take this transaction, include this data, publish the transaction. When the transaction gets included, the code runs, and you notice it says self.domains address.owner equals msg.sender. So what that line of code basically does is it says, whatever address sent that transaction, record that address in the contract storage as the owner of that particular domain. So you notice at the top of the contract here, it says like data domain, so it basically stores a mapping going from a domain to the owner and the IP address of each domain. So the code and the storage, like both of these things are what we call sort of part of the Ethereum state. So what we mean by the state is sort of current information associated with the Ethereum protocol. So stuff that you have to care about right now. This includes account balances, how much Ether you have, nonces, it includes contract code, and it includes contract storage. So for example, right now, this piece of code is nowhere in the state. If I send a transaction, publish a transaction which creates the contract's code is now in the state. Now, if I send another transaction, which then talks to this contract and registers a domain, then the process of executing that transaction is going to change the state. And the new state is going to contain some storage keys that basically say this particular domain has some particular owner and some particular IP address. So that's kind of what the state means. So it's stuff that you have to kind of care about now. So in Bitcoin, for example, the state is pretty simple. It's just like how much money everyone has at some particular point in time. The second thing is history. So history is things that happened. So transactions are part of the history. Receipts are part of the history. Don't have time to go into them, but feel free to research them more. So this is kind of important because a lot of people ask things like, oh, who stores like the transactions, or if a contract executes, then like who executes the contract, so like where are the results stored? And like the answer at this point basically is that if you are a full node, then as a full node, what you do is, number one, you download all the blocks, you download all the transactions. When you receive a block, what you would do is you would see what the state was before the block, then you would execute all the transactions in turn, and you would update your own state. So all full nodes basically execute all transactions, they would execute all contracts, and full nodes, some of them store the history, some of them don't store the history. So like there are clients that are increasingly coming out that let you sort of not store large portions of the history, and this is good because it saves you hard drive space. So the state in Ethereum consists of basically a key value mapping. So basically the state in Ethereum is like a bunch of account objects. And account objects, once again, two types of accounts. One of them is just an account controlled by a person or some external user, controlled by a fridge, controlled by a dog. The other kind of account is a piece of account controlled by code. So these accounts have 4 pieces of data. One of them is the nonce, and that's basically just a kind of highly technical thing that's used to prevent transaction replay attacks. Second thing is a balance, so how much Ether the account has. Third thing is the code. And the fourth thing is storage tree root, which basically points to kind of the storage of that particular contract. So every contract has its own kind of sub-database that it can kind of read and write to as it wishes. Now, contracts cannot write to other contract storage databases. So a contract storage kind of is its own property. The contract, only the contract can actually like read and write to storage that kind of belongs to itself. So also important. So code execution, every transaction specifies a to address. Now, if the to address is just some regular account that doesn't have code, then all you're doing is moving Ether around. If the to address actually has code, then the code runs, and the code can do things. So the code can send Ether from that contract to other contracts. The code can read the contract storage. The code can write to the contract storage. And contracts can even talk to other contracts. So once again, every full node processes every transaction. Every full node stores the entire state. And this is actually fairly similar to how Bitcoin works. It's bold because it's important, as Vlad likes to say in the previous DEF CON. So gas. This is another one of those sort of important misconception points. So basically one of the problems with a kind of extremely free and Turing-complete scripting engine is the halting problem. And the halting problem basically says, given a particular program, if you start running it, there is absolutely no sort of guaranteed way to tell in advance whether or not the program is ever even going to stop. So you might have like program A, which just like does a few things and then stops. Program B, which is an infinite loop. Program C, which is like some kind of highly disguised infinite loop. And you can basically come up with programs where like there is no sort of automated mechanism that can tell which programs are infinite loops and which of them are just going to halt after like a billion steps. So what we do in Ethereum is we have this concept of gas. And the idea basically is that when code executes, we count the number of computational steps that the code takes. And every transaction assigns itself a budget. So a transaction might say, this transaction is allowed to consume a maximum of 1 million gas. So what does that mean? So let's say that this transaction goes to some contract, the code starts running, and one of two things can happen. One of them is, before the million steps run out, execution stops. In that case, everything is fine. Second case is, it gets to 1 million computational steps, then you get what's called an out of gas error. Oh, look, this transaction budgeted 1 million steps, but it already took up 1 million steps, and it looks like it's going to execute some more. It might even run forever, I have no idea. So what I'm going to do instead is we're just going to halt execution right there and just revert the whole thing, and the transaction's essentially failed. Now, for like some technical reasons, even if your transaction kind of fails for this reason, you still have to pay the transaction fee for it. But this is the point of this mechanism is basically that like no matter what kind of weird code you have in the transaction, like it's guaranteed that nodes will be able to process it deterministically within some fixed amount of time. Now, there are other blockchain projects that try to solve the problem with timeouts. So they say try executing the code for 1 second, and if after 1 second it's still running, then you halt. The problem with this approach is that it's not deterministic. So like one computer might take 0.9992 seconds to run a particular piece of code. Another computer might take 1.0008 seconds to run a piece of code. And if the two disagree with each other, then your blockchain has a fork. Gas, completely deterministic computational resource control. So another important thing is that for every transaction, you have to pay a transaction fee for each unit of gas that you consume. So heavier computations cost more. But one important point is that like these two things are separate. So there is like the notion of gas. And the notion of gas is basically just a deterministic method of metering computational resources. And then separately from that, there is protocol economics. And the rules of protocol economics say that if you want your transaction to be included, you have to pay for it. And so if you want to send a transaction to the Ethereum public chain, you have to pay for each unit of gas. If you are doing some kind of like Ethereum-based private network, you do not need to have Ether. So just one important thing that lots of people get wrong that would be kind of good for people to remember. So gas limit, so the equivalent of the block size limit in Bitcoin is kind of the gas limit in Ethereum, 4.7 million gas per block. Now gas isn't just about counting computational steps. You also get charged gas for writing to the state, reading from the state, bytes in your transaction, bytes that you add into receipts, Bloom filter topics. So you get charged gas for kind of almost every resource that you can consume inside of Ethereum. And out of all of those things together, there's this limit that you can't consume more than 4.7 million. So the gas limit actually does kind of adjust automatically, and miners can vote on it. So if Ethereum blocks start getting full, then basically miners are going to be able to kind of just vote the gas limit up, and like no one needs to download any new software. Transactions, 7 parameters. Nonce, so basically prevents replay attacks. So for example, if I send you 10 units of Ether, then what stops you from taking my transaction and including it in a block 10 times to try and drain 10 Ether from my account over and over again? The answer is every transaction has to include a unique number, and once a transaction with a particular nonce is processed, the nonce in the state goes up, and if it tries to verify the second transaction, well, the nonce mismatches now, and so the second time around you can't include it anymore. Gas price, so the amount of Ether you pay for every gas. Start gas is like the amount of gas that you budget yourself. destination address, amount of ether that you send, data. So if you're just sending ether, you don't need to care about data. If you're talking to a contract, then data is readable by contract code. So data is how you specify what function of a contract you're calling, what parameters you're calling it with, anything sort of more complex with that. And VRS, elliptic curve digital signatures. Feel free to research them yourself. I think elliptic curve math is cool. Receipts, not going to bother with those. So Ethereum virtual machine, we have a stack, we have a concept of memory, storage, environment variables. So contracts have access to things like the timestamp. And this is great because you can have contracts that say, if the time is greater than something like January 1st, 2018, then do something. And there's lots of wonderful use cases for this. Logs, calling contracts, calling other contracts. Now, in general, if you're a contract writer, you're not going to be writing in like Ethereum virtual machine code directly. You're going to be writing in higher level languages, so Solidity is the most well-supported one right now. You can also write code in Serpent. There's also something called LLL. So there are kind of other languages that you can write your code in, and then the idea is you would write your code in these languages and it compiles down to Ethereum code. So the code that you write is like nice and readable. The code that is Ethereum code is like extremely compact, fast to execute, blockchain friendly. So ABI. So this is basically that if I actually wants to call some contracts and if I wants to register a domain name, then how am I going to do that? Well, over in the Serpent example, you might notice that I might want to do something like call the setIP function with some particular address and with some particular IP address. So the way that you actually do a call is by sending a transaction. The way that you specify what you're calling is in transaction data, and there exists this nice standardized algorithm called the ABI by which you can encode the data. So the first 4 bytes represent the function ID, then 32 bytes for the first argument, then 32 bytes for the second argument. If you have variable-sized arguments, it gets more complex, but feel free to research this. So we have a new mining algorithm, and this mining algorithm strives to be kind of memory hard and GPU friendly. So the goal is to sort of prevent ASICs or prevent specialized hardware from like being the dominant force in mining because that would make mining too centralized. But at the same time, CPU mining has other issues. So we have this sort of GPU mining that's a nice middle ground. It's a fairly pretty algorithm once again. It's called ETH hash. So fast block times, Merkle trees. So this is also a kind of very important piece of the Ethereum protocol. So the reason why I have this picture here is because about a year ago there was this cover in the New York Times that basically have Life Masters that's saying it's all about the blockchain. And personally, I think it's not just about the blockchain, it's about the Merkle tree. And I think Merkle trees are like awesome and really important. So we should have Ralph Merkle saying it's all about the Merkle tree, and you should have some Doges because Doges are cool. I hope it's not a violation of securities law to say that Dogecoin is awesome, and if you want to buy it, you can. Cool. So Merkle trees, the point basically is, so this is how the Ethereum Lite client works. So the problem is, okay, if you have the entire database, if you have the entire state, if you have all the transactions, then you can know, let's say, what your account balance is, what some particular contract's code is, what some particular contract storage is, what some particular log says. But what if you're a light client? What if you're on a phone? What if you're on an IoT device and you don't have enough resources to process the entire blockchain? So the blockchain itself, right now, the blockchain is 3 bytes. The sort of state size is something around between like 5 and 20 bytes, depending on which client options you use. So it gets pretty big for a phone. So if, let's say, you have a tiny device that has like 50 megabytes and very low processing power, then what do? So this wonderful fellow came up with this algorithm where basically what you do is you store this kind of really clever hash tree where you store the pieces of data at the bottom, then you like have hashes of those, and you have hashes of hashes and hashes of hashes. And the end result is, if, let's say, all that I care about is getting key for, let's say, some like this particular key of this particular account 175, then you don't actually have to download the entire blockchain yourself. Instead, all you do is you download this, what we call kind of this Merkle branch. You verify that the hashes inside of the branch are consistent. And as long as you have the block headers, you just kind of verify the Merkle branch against the block headers. And what you're doing is you're essentially allowing the miners to kind of help you verify that this particular piece of the state actually is what the node says it is. So if a node gives you a Merkle, this sort of Merkle proof that says this particular key in this particular account is 45, if you can verify the proof of work and you can verify the hashes, then basically you can verify that unless like all the miners are at that particular time conspiring to screw you over, this actually is what the state of the blockchain is in this particular place at that time. So the Light client, there was like a test, an alpha version that was released a couple of weeks ago. I've tried it, it works great. So block headers contain 3 trees. So Bitcoin uses Merkle trees just for transactions. We use Merkle trees for transactions for the state. So this includes account balances, contract code, contract storage, receipts. So we have Patricia trees, which allow you to kind of update the tree very efficiently. And so those are kind of the basic building blocks of the Ethereum protocol right now. There's also very fun stuff that we're working on in the future. So things like proof of stake that I'm going to, and scalability that I'm going to talk about in my presentation later today. Privacy support. So basically, with privacy, you don't have to actually build things into the base protocol. Because the Ethereum protocol is Turing complete, you can basically like implement any kind of advanced cryptography on top of it. Now, for like VM efficiency reasons, there are still sort of protocol tweaks that we have to make, but even still, it's something where like the vast majority of the work actually does sort of happen on the higher levels. Virtual machine upgrades, sort of more flexible use of storage and scalability, and these things are great. And just to set a good example, I'm going to stop now because the clock tells me to stop now. So thank you.